we are going to now calculate that multi-level system with fixed energy. Now, that is another constraint that we are adding. Earlier the constraint was that total number of particles is n, I divide into 3 levels, 4 levels, 5 levels, and fine with that. Now, I have an additional constraint that I have a fixed amount of energy. Earlier all energy levels were all equal. Now, I can have different energy levels, some higher level, some lower level, and in that case how we can address those problems. So, those problems are similar to putting r indistinguishable particles or balls into n boxes. So, r indistinguishable balls, which are like we will say that as energy, in n boxes which are particles. We will come back to that. So, now we are talking about distribution of energy. Energies are indistinguishable, by the way, okay, because energy is just unit of energy. We cannot associate this energy as a green energy or a blue energy and things like that. Energies are indistinguishable. So, let us say I have 3 distinguishable particles and 3 units of energy which are indistinguishable. So, this problem is, as I discussed before, putting indistinguishable particles in distinguishable boxes. I will just remind you, it is like you have 3 distinguishable boxes and you are putting 3 indistinguishable particles. I did not color them, they are indistinguishable. So, here I am saying that this is our energy and this is our particle. Why? Because particles are distinguishable and energies are not. That is why we have arranged that. So, in probability we can take any possible choice we like. Since our energies are indistinguishable, we have considered energies as the indistinguishable particles, and since our particles are distinguishable, we consider them as distinguishable boxes. Then it boils down to putting indistinguishable particles in distinguishable boxes. The same statistics we can apply. So, I will show you that. For example, let us say 3 distinguishable particles are there and we need to put energies into that. So, how many ways we can do that? I will just show you in a moment. So, let us say I put one particle with 3 units of energy. So, I can put the 3 units of energy. So, these lines denote energy. So, I can put 3 units of energy around only one particle. So, I can put that around red particle, I can put that around green particle, I can put that around blue particle. So, of course, I have 3 ways of doing so, right. Now, my distribution B, in which I put one particle with 2 units of energy and another particle with 1 units of energy. How many ways I can do that? My 2 units of energy I could have chosen for any of the 3 particles, then rest I could have chosen for any of the other 2 particles. So, I have 6 ways of doing so. Is it clear? Now, the last distribution is each particle has 1 unit of energy. Can I do in any other way than 1? I can do only one way. So, you see I have now 3 possible distributions with the constraints that total number of particles are 3, total number of particles is 3, total energy is 3, I could get 3 distributions and I could get a total of 10 possible ways. So, my W tot is 10. So, my probability of this distribution A is W A by W tot, which is 3 by 10. Probability of distribution B is W B by W tot is 6 by 10. Probability of C, which is W C by W tot, is 1 by 10. So, which is most probable distribution? Distribution B is the most probable distribution, because it has the highest probability. That is why it is most probable distribution. So, if you have 3 units of energy and 3 distinguishable particles, then most likely what will happen is that one particle will get 2 units of energy and another particle will get 1 unit of energy, another particle will not have any energy with it. So, again this is figuratively speaking, because again as you see probabilities are not that widely different, 6 by 10 and 3 by 10, one is double of the other, another is 6 times of the other or 3 times of the other. However, as you know, with more and more particles and more energy units, the number of distributions will increase, and most probable distribution will be much more probable than the other distributions. So, I will give you a realistic example of different possible energy values in a realistic situations where a particle can be in a different possible energy values. And one of the classic example is vibrational motions or known as like quantum harmonic oscillator. So, I know in our classical, you know that in your classical oscillator, your is like a spring that shrinks and expands under a potential. Okay. So, same kind of potential, if you use to solve Schrodinger's equation, then you will get a solution in which the energy values will be spaced equally, such that the energy of one particular level is or one particular level EV will be V plus half h nu or h cut omega. So, again, so that is shown here. So, these are quantum labels. So, in chemical principles 1 we discussed about that how one can get quantized energy, that the potential energy is important in order to get different effects, and quantum harmonic oscillator is solutions where the potential V is half k x square, where it is bound, it is like a spring where it is bound on one side. So, one side is held and another side will move. So, also you can think of the distance between the proton and the electron as described by a quantum harmonic oscillator thing, but although it is not exactly the case because the potential is actually different, but one can get the similar idea that why there will be different levels. So, in quantum harmonic oscillator case, it is just half k x square is the potential, and then you get different levels of equal spacings. So, which means that if you are in the ground level, you have some energy values, and you move like little bit from here, you move this much, but in the first excited level, you move farther apart with higher energy, third level you move farther apart with higher energy. The bottom line is, this is an example. Right now we are just treating it as an example of different energy levels in which a particle. So, what do you mean by a particle? You can say a quantum state. The state of the system is now in one of the level. Okay, you can think about that way, or when you solve for an electron under the harmonic potential, it is just one particle in the potential, and it can be in different levels. So, this is an example of one particle in different energy levels. So, we are talking about multiple energy levels, but with one particle. So, n equal to 1 is shown here. So, these V zeros, so this V 0, V 1, V 2 are and V 3 are different vibrational levels, and the particle can be in any of them. So, we are talking about one. So, remember we discussed about one particle in a box, and that time we said only one possible ways to do that, because the box has one value of energy, the accessible states were only one. So, here we are showing that particle number less, but many more accessible states, which will give rise to more entropy, because now same particle can be in any different states. For example, earlier we talked about n equal to 210 particles, 3 boxes. So, accessible states were 3, number were huge. Even if we had one particle, one particle could have been in any of those boxes. So, there are 3 possibilities could have come. Here there are infinite possibilities, because the particle can be in any of these levels. Okay, infinite possibilities with just one particle. However, if we say that and each one will give you 1 microstate, right. So, whether it is in 4 or it is in 5 or it is in 3, it will give you 1 microstate, right. But if we say that the energy is fixed, let us say if I say that, okay, what is the number of microstate for one particle in the harmonic oscillator when the energy is 4, then there is only one possible ways to do that, right. We cannot have multiple possible ways. The fact that we are getting more number of microstates because more accessible states are there and there is no constraint. So, now I will show you the similar situation where accessible states are more even for one particle, and the example is particle in a 3D box. So, particle in a 1D box again had the similar energy different energy levels like harmonic oscillator. Similarly, particle in a 3D box also energy levels are not equally spaced, but we are giving you an example where one particle can have more accessible states and therefore more degeneracy even when the energy is fixed. So, harmonic oscillator case, what we say, one particle, if the energy is fixed, then can have only one possible ways. One particle, nothing fixed, no energy is fixed, then there are infinite possible ways one can do that for harmonic oscillator. But particle in a 3D box, interestingly you can see that. So, we can write that energy as nx square plus n square plus nz square, h square by 8 m l square, where L is. So, we are talking about 3D box which is cubic box where all the 3 lengths are same. H is a constant, m is, let us say, it is an electron, so it is constant, L is, let us say, fixed. Even then we have this quantum numbers nx, ny and nz. So, it is dimension. So, we have now increased the dimension of the system from one dimensional harmonic oscillator to 3 dimensional box. And here an interesting thing happens that, so you know that nx, ny and nz, they can go from 1, 2, 3, 4, 5, all integer number they can take starting from 1. It cannot have 0 though, unlike the harmonic oscillator where it was 0 is also possible. Now, if you put those values, you are going to get different energies. So, let us put 1, 1 and 1, we will get energy as 3 units is h square by 8 m l square, we get 3. How many possible ways we can do that? Only one possible way. Now, let us put 1, 1 and 2. So,
energy becomes 6 and there are 3 possible ways to get that.
So, again if I now one particle system energy value fixed. Earlier for harmonic oscillator, for one dimensional harmonic oscillator, we would get only one microstate. Why? Because one dimension, one particle, one energy level. Here one particle, one energy level, but 3 dimension, and we are getting more number of possibilities. We are getting 3 possibilities for 3 possibilities when the energy is 6, again 3 possibilities when energy is 9, and we are getting 6 possibilities when energy is 14, and many more. Probably we will get more possibilities when energy increases. So, the point here is that either the dimension or the number of particles or the accessible states, if any of them changes, then that gives rise to more possibilities, more number of microstates, and this quantity denotes the number of microstates for a given energy. And you can see that number of microstates for a given energy also increases. So, W will increase the number of microstates for a given energy will increase with E. That is a very interesting point that we will come back later on, that for a given value of energy, the number of microstates that we calculate will increase with the value of energy, which means that since the number of microstates is increasing, which means the entropy is increasing. So, entropy will increase with energy, and that is also taken as a postulate when the postulate based thermodynamics is used, and you will see that it is related to the temperature. Yeah, so it is related to the 1 by temperature. So, the number of microstates energy. So, now let us talk about 2 harmonic oscillator, like 2 particles. Each harmonic oscillator has equal spacings, just like we had discussed before, and that time what happened is that if the energy level was fixed, then number of microstates was just 1. But now I have just increased the number of particles to 2 and the number of harmonic oscillator to 2 as well, just like this situation where one harmonic oscillator has this equal spacing in which the blue particle is sitting at some level nu 2 equal to 1, and I have another harmonic oscillator in which a red particle is sitting at some level, giving this rise to this number. Now, ideally this red particle can be anywhere here and the blue particle can be anywhere here, but I give a constraint that how many microstars are there for a total energy of 3 h cut omega. Now, in order to get that, let us write down the number. So, V1 gives me V1 plus half h cut omega, and V2 gives me V2 plus half h cut omega. So, the total energy is V1 plus V2, giving me V1 plus V2 plus 1 h cut omega. Now, I need to get V1 plus V2 plus 1 equal to 3. Therefore, V1 plus V2 I need to get as 2. So, once I do that, so that means now I have to see that which one can give me 2. So, 0, 2 can give me a 2, 1 can give me a 2, 2, 0 can give me a 2. So, now I can get actually 3 different ways to get that total energy 3 h cut omega I can obtain by using this particular rule. So, basically I have to kind of a partition my number, integer number 2 into 2 different levels, exactly 2 different levels. I partition my number. So, when I talk about partition a number, so I have said that my total number is 2, and then I have to say that 2 is divided into 2 parts. It can be 0 2, 1 1 or 2 0. So, this will give me 3 different possibilities. So, now let us talk about that distribution of energy and distribution of energy into boxes. So, remember I said that distribution of indistinguishable particles to distinguishable boxes, we discussed about that. Here the indistinguishable particle is energy and distinguishable boxes are particles. Because because the particles are distinguishable, we consider as box now, and because energy is indistinguishable, we consider that as a particle now. That is the whole idea. Okay. The idea is that you put indistinguishable things into distinguishable things. Okay. So, there will be how many possibilities. So, we will come to that, this particular part will come to that. So, we are back to the same problem. Remember that we said that 3 units of energy and 3 particle, same situation we came back, but now instead of drawing with lines, we are drawing as energy levels. So, let us say there are 4 energy levels available, 0 1 0 1 2 and 3, and there are 3 distinguishable particles with 3 colors. How can we do that? You see, I can put 2 particles in 0 level and 1 particle in level 3, that will satisfy my total energy, total particle is satisfied and total number of states are also satisfied. Second possibility is that I can put 1 particle in the level 2, another particle in level 1, that will give me a total of 3 units of energy, or I can put all the 3 particles in level 1 itself, that will also give me total energy 3. So, here we are talking about distribution when the total energy is constrained, that is the idea, distribution of distinguishable particles in different energy levels when the total energy is constant, and that is what we are trying to do. Of course, as you can see that I can put at this level any 3 of the particle and that gives me 3. At this level 2 I can put any 3 of the particle for which I can put any 2 particle here and that gives me 6, and I have no choice but to put all the particles in this level, and therefore, I have only one choice. So, this is our earlier distribution A, distribution B and distribution C that we discussed before, and the corresponding probabilities that we talked about before, giving me this as my MPD, most probable distribution. You see, interestingly, notice one thing, the most probable distribution is the one where particles are all in different levels, and we will see later on that particles would like to be in all different levels to increase their entropy, unless they are constrained by something else to be somewhere, then it will change. But if you have no constraint, then particle will like to be in all different levels, because that will increase the number of microstates and therefore entropy of the system. So, this is the same thing that I discussed, that I will just clear this part so that you can see that ideally we will say that the total number of distribution is 10, as I said, W tot is 10 because you can add them, and but the most probable distribution is 6. So, ideally we should write the entropy as KBL and W tot, but we will use distribution B only, which is most probable distribution, to calculate the entropy, since we will show that WMPD equal to W tot for a large number of. We already have shown that for 2 level system, and it is true for multi level systems as well. We have already shown that. So, it is not that we will show. So, basically we already showed before by showing that.